Welcome to this explainer. As a systems reliability engineer, or SRE, I literally spend my days obsessed with high availability server environments and, well, performance tuning. Today, we're going to take that exact same architectural mindset and apply it somewhere a little unexpected. Chemical solutions. We're going to treat them as complex systems that require absolutely precise resource management. Think of chemical concepts like dilution and trace units as deployment cycles and system diagnostics. It's kind of like a giant puzzle. Let's dive right in.
Here's our technical roadmap for today. We'll start with resource resizing and scaling logic, shift gears into trace telemetry and error rates, and then wrap the whole thing up with system breakpoints.
Okay, Section 1, Resource Resizing and Scaling Logic.
So, in software engineering, when we want to save memory, what do? We downscale a server instance, right? Well, in chemistry, we perform an operation with that exact same logical goal. We call it dilution. Notice how we can draw a pretty strict binary here to understand this system. On one side, we've got the payload mass. In a chemical solution, this is your solute, the active ingredient you actually care about, and it's measured in moles. On the other side, we've got the environment volume. This is the solvent, usually water, measured in liters. The payload mass, totally static, but that environment volume, it's highly variable. This physical demonstration brilliantly illustrates the whole concept. Take a look at these two graduated cylinders. We have a blue liquid, copper nitrate. Now we have the exact same amount of the active blue payload in both cylinders, but the environment volume on the right has been heavily scaled up with water. We are absolutely bound here by an unbreakable physical law. If you add more solvent to a container, the molarity decreases, but the payload mass remains completely identical.
Moving right along to Section 2, Universal Laws of Downscaling.
Now, the absolutely crucial point here is the formula governing this transition. It's the dilution equation, M1 times V1 equals M2 times V2. This essentially equates the initial state of your concentration and volume directly to the final state. It represents an immutable logic, okay? If the number of moles stays constant, the product M times V remains entirely unchanged.
And that brings us to a perfect equilibrium. Because the dilution process doesn't change the physical amount of the solute, the initial and final system states are perfectly equalized. N1 equals N2. The total number of moles of payload at the very start of your deployment is the exact same number of moles at the end. Only the environment size has shifted.
All right, Section 3, Predicting Future Deployments.
We execute this in 3 highly structured steps. First up, you set your initial state, documenting M1 and V1. Second, you define your final volume, V2, which is basically just how much you're scaling the environment. And third, you calculate the new molarity, M2. This allows us to confidently predict our future state. If we set the initial volume to X, the final concentration will drop to Y. Or, to put it more in laboratory terms, if we dilute this stock solution correctly, it will hit the target concentration for the experiment every single time.
To summarize this mechanism, our source text notes, and I quote, "Dilution is the process whereby the concentration of a solution is lessened by the addition of solvent. The real key takeaway here is about maintaining absolute volumetric precision. When you standardize your stock solutions, you're setting up a totally reliable base so that all your future downscaled deployments execute flawlessly."
Which leads us to Section 4, Trace Telemetry and Error Rates.
Transitioning to systems where the payload is incredibly small poses a pretty massive architectural challenge. I mean, how do we measure when the data signal is infinitely smaller than the system noise? Think about it. If we're tracking microscopic error rates or trace contaminants in massive environmental volumes like, say, a municipal water supply, standard molarity units completely fail us. They're just way too large to be useful. To solve this, we introduce trace telemetry units. Up in the top row of our matrix, we have ppm, which you read aloud as parts per million, or simply ppm. This carries an exponential mass multiplier of 10 to the 6th power. Right below that is ppb, or parts per billion, with a multiplier of 10 to the 9th power. We rely heavily on these exponential scales when our chemical signal is literally just a tiny fraction of the overall system mass.
Let's look closer in Section 5, Signal versus System Noise.
We can actually anchor this concept in a really vital, real-world metric based on the density of water. 1 ppm translates perfectly to 1 milligram per liter. This is literally a foundational law of our telemetry. If a system registers 1 milligram of solute per liter of water, the telemetry reads exactly 1 ppm, no exceptions.
Let's bring this right into your kitchen. On the left, you've got raw output from a standard faucet, which might actually contain trace-level contaminants. On the right, we see an inline water filter dispenser in a refrigerator.
we can predict the remediation of our system errors using our telemetry. If we install this inline filter correctly, it will successfully reduce the trace-level contaminants in the tap water system, catching that signal noise way before it ever reaches the end user.
Finally, Section 6, Thresholds and System Breakpoints.
So in software, a breakpoint is a targeted pause in your system execution that you use for debugging. Well, in environmental chemistry, the EPA sets these breakpoints. For instance, the maximum safe level for fluoride in tap water is 4 ppm, but for highly toxic payloads like lead, the remedial action limit is an incredibly strict 15 parts per billion. If our trace error telemetry hits these limits, it is a critical system breakpoint. System execution must halt, and the system must be patched.
I really want to leave you with this final, somewhat provocative thought. In any complex architecture, survival depends not on the size of the environment, but on the precision of your breakpoints. So what happens when an undetected trace error completely overwrites your system state? Whether you're managing memory allocation in a massive server cluster or analyzing parts per billion of lead in a city's water supply, the necessity for precise performance tuning is exactly the same. Thank you so much for joining me for this explainer, and I hope you're eager to go out there and analyze the telemetry in your own environments.